Okay, so let's summarize what we have learned last time, and today we are going to talk about the vector field and the integration of vector field. So, when you have a function defined on some two-dimensional domain, and it's a real valued function, and let's say we have a curve which has a starting point and end point. These starting point and end point could be the same point. That means it's a closed curve on a plane. And if you want to integrate these two variable function over this curve, that means we're trying to get an area under the section of a graph over this curve. So it's a two-dimensional area. And it is written in this symbol, and we are going to define or calculate this integral by, let's see, f composite c. So this gives one variable function, and then multiply that with, let's say, I put t here, and then multiply that with the speed of the curve, parameterized curve c, and then dt. Okay? So that's the definition, and we have seen that this definition, this formula does not depend on the way we parameterize the curve c. Okay? So you don't have to worry about whether you are given with a set of curve or a curve as a set of points, then no matter how you parameterize your curve, the results are the same. And today we're going to talk about first surface integral and then the integral of vector field. So let's talk about the surface field, surface integral. Again, we are going to define a function. Now it's a three-variable function defined on three-dimensional domain. And we are going to define a parameterized surface named as S. And let's say we're going to parameterize that surface using two variables. One is called u and the other is called v. So let's say I'm going to find out, let's say this is our surface S in three-dimensional space. And if you have a two-dimensional surface in three-dimensional space, you have two freedom of choice to define a unique point on the surface. For example, you can give one direction of axis line and the other direction of axis line. And by looking at the value or the label of this vertical and horizontal line, you can identify a unique point on the surface. So you can translate your coordinate system on the surface in this way to the plane, uv. So for example, I'm going to map these red curves to the vertical lines on uv plane, okay? And then these green curves to horizontal lines. And we are talking about the surface which is bounded. So our grid lines are also bounded. So if you have a map S doing this transformation. Let's say I'm mapping my my point on UV plane, which is at the second red line and the second green line, to the point on the surface. You just pick the second green line and second red line on the surface grid here. So this is our parameterization. This is called the parameterization of a surface. I will going to give a concrete example after I finish defining the surface integral. So whatever we do when we do surface integral is, now this is just a set of points which consists the surface. We have a function defined on three-dimensional space. Suppose that our volume V, the domain of F, contains entire surface. So for example, I can put my surface into very large, so very large box here, right? So let's say this is our V. So that means I can find the value of function for any point on the surface S, okay? So I'm trying to find out the mass of the surface if my point density is given by the function f. Okay, so it's the same idea that we define the double integral. So if you think about double integral, maybe a triple integral. Okay, so if you remember how we interpret the triple integral of a function, we define that the value of triple integral is the mass of the volume, considering the function integrand is the point density of the point inside of the volume. So here we're talking about the volume, but not going to integrate the entire volume, but only the two-dimensional surface inside the volume. Okay, and still we are talking about the point density function f. So that means if I add up all the small masses of the surface, then I get entire mass of the surface. And in order to get a small mass of small portion of the surface, I need to find out the area of this small portion of the surface and then multiply that with the point density to get approximate mass of the surface. Okay? So I'm going to write my symbol like this. So we have, let's say this is a large S. Okay, so large S is used as symbol for representing the set of point, which is a surface inside of three-dimensional space, and also a function which parameterizes that surface. Okay, so I'm going to put a double integral, and that integral is over the surface S. This S is basically the set, and we're going to integrate f, and then I put ds. Okay, so that's the notation for the surface integral. I'm going to name it the surface integral of function f over s, and it means that it's the mass of the surface S with the point density function f. Okay. So let's try to find out how we can compute that actual mass. So we have to start with the meaning first, okay, and then try to retrieve the formula that computes that meaning. All right, let's look at this small portion again. So again, this small portion corresponds to some rectangular region inside of this UV domain, because S, let's say we are talking about A to B times C to D here, okay? So we are mapping a rectangular domain to some curved surface inside of three-dimensional space. But this rectangular domain is already a two-dimensional space. If we are taking a small portion here, corresponds to small rectangular region in this domain, then what's the ratio between, how do we get this area? How do we get this small portion, area of this small portion? So this area of S corresponds to this small area in UV plane, right? But these two areas are not the same. But we can find the ratio between these two areas. What was we actually covered that. Jacobian, right? So we can multiply Jacobian to one area to get another area, right? So let's talk about it in more detail. So first of all, I want to subdivide my S into smaller pieces. So to find or to compute my surface integral, first you need to subdivide S into sum of Sij, where Sij for each I and j is the image of our parameterization corresponds to this small portion, right? Dij is a small portion of rectangular area inside the domain of UV plane, and this is equals to ui plus 1 and vi plus 1. Okay. Now, if I have to be more concrete, I can define my ui. And ui is a plus I delta u, and delta u is b minus a over n. And also vi is c plus I delta v, and delta v is d minus c over n. So I'm basically dividing my AB interval and CD interval into n subintervals, and then try to label that from 0 to n minus 1, and I from 0 to n. Okay. And then let's try to find the area of Sij. And as Hyungyu said, as Hyungyu said, this area is approximately area of Dij times the Jacobian, but let's say, what kind of Jacobian should we use? So, because we can consider S as a transformation, but sometimes it's confusing to whether we should choose S as a transformation or S inverse as a transformation. But you have to remember another form, symbol for the Jacobian, that this lies in Sij let's say this Sij lies in XYZ space and Dij lies in UV plane. So oh, maybe not. So sorry. So we cannot apply the Jacobian directly because this S is not the function from R2 to R2. This is from R2 to R3. Whenever we try to use the Jacobian for transformation, that transformation must be a function, one-to-one correspondence function from Rn to Rn. The dimension should be the same. Here we have different dimensions. We have two-dimensional space for domain, three-dimensional space for codomain. So we cannot use the Jacobian. You cannot define the Jacobian. But so we need some factor here. But idea is the same. So let's try to find these factors that should multiply to the area of Dij to get the area of Sij. Let me make a big picture of small portion. Here is our ui, vi, and here is our vector. Okay, so I know that this length is delta u and this is delta v, and therefore this vector is what? Delta u 0, and this is 0 delta v. Okay. Now, S maps these horizontal line into some curved line in three-dimensional space. So let's say I'm taking ui, vi to xi, not xi. Let's see. So let me just replace this point to uv for now, because I can add my ij information later once I talk about this, what's going on inside of this parameterization. So let's say uv is mapped to x, y, z here, okay? And then what happens when I follow this horizontal line? So this line is parameterized by C1t equals to what? Delta ut, comma 0. And if I follow this vertical line, let's say this is C2t, that means it's 0 delta vt, right? So I am at the end of this subinterval when t equals to 1, and this is when t equals to 1. I at another end of this subinterval. Now, I started from x, y, z corresponds to uv, and the curve that I follow is S composite C1. And if I follow C2 curve, then the corresponding curve is given by S composite C2. Okay? Now, the actual area is a curved area like this curved area, right? This is the small portion of S, which is Sij, and this is Dij, okay? But we cannot find actual area of a surface, curved surface. But since we are talking about very small delta u and delta v, I can approximate this curved surface as if it's just a parallelogram in three-dimensional space. So let's say I'm going to find a vector which approximates the tangent vector of each curves here. And what's this curve here now? This is S composite C1 prime 0, and this is S composite C2 times 0. Okay? So, and then if I find the area of this parallelogram, then this is approximately equal to the area of Sij. So I exaggerated the picture, but if you keep enlarging your surface, then it's almost look like the plane, and it has almost zero error when you approximate your area of a surface to area of the parallelogram. So let's try to compare the area of parallelogram in this three-dimensional space and the area of a rectangle in the UV plane. So area of Sij is approximately the area of parallelogram bounded by two curves, two vectors, 0 and SC2 prime 0. So let's try to find out what these are in real. I'm going to write my function s in this way. So s is mapping uv to xyz. So xyz has its own function in two-variable function. So that is the formula of the s. So this gives that I'm going to take the part ddt of, it's a single variable function, by the way, of what? So by taking x in C1 here, delta ut 0, y delta ut 0, and z delta ut 0. And when you take the derivative of this three coordinate, you take the the derivative of t for each coordinate. So what happens when you take the derivative of this kind of function? This is a composite of two multivariable functions. First, therefore, you should use the chain rule. First, you take the integration of the outside and inside. Or you can use the formula of a chain rule directly, that first you take the partial derivative of x by the first variable of x, which is u, so xu. And then I'm taking, so I'm taking a derivative at 0, so I'm going to plug in 0 here. Right, 0, 0. Oh, by the way, so sorry, so I should put this plus uv, right? As a curve, I need to specify the starting point, right? So when t equals to 0, so let me write it here again. So this is u plus delta ut v, and y u plus delta ut v. The uv is constant here. So u plus delta ut v. And then first you take the integral on the first coordinates of x, then you get xu, and you plug in t equals to 0, you get u comma v, and then you multiply the partial derivative of the first variable inside of f by t, which gets delta u. But then you have to take the partial derivative of x by second variable, which is v, but it will multiply by the derivative of v by t, but v is constant, so it gets 0, so nothing happens afterwards. So this is our result. How about here? We get yu uv delta u, and that's zu uv delta u. So basically, the vector, the first vector is xu yu zu times delta u. And I can abbreviate my notation XU, YU, ZU by SU, because S is used as the function that has 3 coordinate systems here. So I can just abbreviate my notation, these thing as SU times delta U. And what happens to S composite C2 prime 0? So it's almost same, except that we have T components on the second variable. So everything is changed to V here, because partial derivative of U disappears, because we are going to take, if you take the derivative of T of the first coordinate, which is U, then it gets 0. So this is equals to xv, yv, zv times delta v, and this is equals to sv delta v. So we get we had 2 vectors in 3-dimensional space, and in order to find the area of parallelogram bounded by these 2 vectors, we need to take the cross product. So the cross product of these 2 vectors, SU delta U cross SV delta V. So generally, cross product gives you the vector, but area is the size of that vector. So is equals to SU cross SV. So as delta U, delta V are scalars, so that can be pulled outside of the size of vectors. So delta U and delta V. So we know that delta U, delta V is the area of Dij. So this is equals to SU, SV, area of Dij. So this is the area, approximate area of Sij. We needed this vector, and we found that that vector is given by SU, SV. So we are talking about that thing on these points, so we can replace my UV as UI, VI. We can make the same argument. Then we know that this vector is the norm of a vector obtained by cross product of 2 vectors. One is SU at UI, VI. The other is SV at UI, VI. Okay? If you get 2 vectors at one point and then take a cross product and take the norm, that is the factor that that makes this approximation equal. Okay, so let's try to finish our argument. So we had the meaning. Now we need to find the formula. So total mass of S is approximately sum of all area of Sij times the density Fi Vj, right? So you can take Ui, Vi at the left lower corner of the point, but you can also choose any point inside of this domain, or maybe x xij, yij, and zij here. So we have a double index here. These point is a point inside Sij. Okay. So this is area and this is density. So this gives the mass of small portion, and if you add these, then you get entire volume. But then I'm going to rewrite in terms of everything in UV variables. So area of Sij is equals to Su Ui Vj times SV Ui Vj. That's the factor times the area of Dij, and I can rewrite that as delta U, delta V. And how about the mass? So in order to find a point inside of Sij, since we have a one-to-one mapping between the surface and rectangular domain in UV plane, I can find a point inside of Dij here to identify a point inside of this small portion. So I can choose some point Ui Vj star. So that's the point inside of Dij. And then send it to a point in the surface by the parameterization of the surface S. So we have a composite F and S. You cannot directly plug in Ui star and Vj star to the function F because F is a 3-variable function, okay? F is a 3-variable function. You need to find the value by this transformation. So let's observe what we have done here. We have everything in terms of U and V. You have du, dv, and we summed over ij, where ij independently runs from 0 to n minus 1 to cover the entire surface, right? That's similar to the double integral, right? That's the Riemann sum for the double integral. So, therefore, total mass is equal to what? Double integral over which domain? So where does Ui runs for? Runs from A to B, right? Vj runs from C to D. So we are doing the double integral on the domain of S. And what's our integrand? First of all, let's write this first. This is the value of function, but not directly putting f because f is 3-variable function. We're taking f at composite S to make it 2-variable function on UV plane. And then we multiply that with what? This function. This is again 2-variable function in terms of U and V. Okay? Su cross Sv. And du dv. Okay? So total mass of S is this. So therefore, the surface integral, written as Sf ds, is computed in this way. Okay? So this is the definition somehow. If you take a more general statement, if you want to take a more general statement, the domain of S doesn't have to be rectangular domain. If you can find another parameterization from any type of domain in 2-dimensional space, then you can replace the domain of integration to whatever the domain of the parameterization of the surface. But let's leave it here. Let's look at some example. So if the density is 1, then the mass is equals to the area of the surface. So let's assume that the density is 1 and try to find the area, find the mass of the sphere, and then try to compare that with our known formula. So I'm going to define S to be parameterization of the sphere, unit sphere. So this is for theta, and this is for phi. And I'm going to map into three-dimensional space. So S theta phi is given by, first, when you're talking about the spherical coordinate, you need three independent variables. So I'm missing rho here, but I'm fixing rho as 1 because I'm talking about point on the unit sphere, on the surface of unit sphere. So I'm not going to put rho as an independent variable. So if rho is fixed as 1, then this is now sine theta cosine phi, and sine theta sine phi, and cosine theta. Okay. So I'm taking a sphere of radius 1. So whenever I have point on the sphere, this is our theta, and if I project down onto xy plane, this is x, and this is y, then this is my phi. Okay? Let's try to find out what is the surface integral of 1 over the surface S, parameterized by this way. So let's try to put that into our formula. So I'm going to make it into double integral over 0 to pi of 1. Well, technically, I have to composite that, but 1 is constant function. So even if I composite one function with any parameterization, it will always become 1. And then I have to take the norm of SU cross S phi. So here UV is written as theta and phi. So I'm going to put S theta cross S phi. Okay. And then d theta d phi. So I need to find out this function. Now let me write it here. So first, S theta is the vector that obtained by taking a partial derivative of theta on these coordinates. So we get cosine theta, cosine phi, and cosine theta, sine phi, and minus sine theta. And S phi is minus sine theta, sine phi, and then sine theta, cosine phi, and 0, right? So let's take cross product. So cross product S theta, S phi. Let's take first the cross product first, and then take the norm later. Is the determinant of 3 by 3 matrix. So this is how you remember the cross product. I always talk, as I always emphasize. So cosine theta, cosine phi, cosine theta, sine phi, and minus theta, and minus sine theta, sine phi, and sine theta, cosine phi, 0. So here we have j and k. So if you take the cross determinant of 3 by 3 matrix, let's try to look at whatever that contains I in the factor. So it can be obtained by this way of multiplication and these multiplication, but you see, 1, 2, right? So you see, this one has 0, so it doesn't occur, and this one has a negative sign, so we get sine theta square sine phi, okay, times I. And what about j? So you get 0 in this way. You get this thing again. So it's a minus sine square sine. Sorry, this is cosine, right? And sine phi j. And then what happened to k? Let's write it here. So sine square sine phi j. And what about k? So k is obtained by two factors. We have multiplication, these multiplication, and these multiplication. But if you multiply this and then subtract the multiplication of these, then you get sine theta cosine theta, but cosine square phi plus sine square phi. So we have a canceling of sine square plus cosine square equals to 1. So we get plus sine theta cosine theta k. Okay. So that's our vector, the cross product. We're not going to plug in that here. We're going to take the norm of that vector. So norm of that vector is, yes. J. Oh yes. So this way, right? Plus. Yeah. Thank you. And this is equals to square root of square sum of these absolute the components here. So I deliberately wrote ijk here, but you have to remember that I is equals to 1, 0, 0, j is equals to 0, 1, 0, so k equals to 0, 0, 1. So basically it's sine square cosine, sine square sine, and sine cosine, right? So if you square these two and then add it together, so then you get s fourth, and also you get s square plus s square cosine square. But then you have s square factors, common factors, and you get s square plus cosine square. So whatever you're left with is s theta, sine theta. Of course, you need an absolute value, but I omitted it because theta is from 0 to pi, so it's always positive. So therefore, the surface integral is integration of 0 pi 0 to pi. So I can change my double integral to iterated integral because our integrand is the sine function, which is continuous function. I can use the Fubini theorem. So sine theta of first, this is for phi, and next this is for theta. So if I integrate my phi, then we're integrating a constant function I can take out. So and then if I integrate my sine theta from 0 to pi, we get 2, right? So this is 4 pi. So it makes sense, right? Because this is the area of the surface. Although we are trying to get the surface integral, which gives the mass, but we are taking the density as 1, so the mass is equals to the area of the surface. Okay. What else you want to find out? What other surface you want to find out for the surface integral? Let's see. I'm going to have a hemisphere on three-dimensional space, and I'm going to take that as my surface S. Okay, so no bottom here, so only the upper hemisphere, and my function defined on the three-dimensional space will be just x. Okay, or maybe z. Okay, so maybe let's z. So f x y z is z, and then my s is upper hemisphere. So let's try to find out the surface integral of s, f at s. So what do you need to do first? So you want to apply this formula. What do you need to do? Define what?
Define the coordinates so that we can map.
Right, define the coordinate, exactly. So you have to find out the parameterization of S. So let's say I'm going to parameterize the same way we did for the sphere, because it's simply the half of sphere. So this will be sine, cosine, and sine, sine, cosine. And next,
And then find each derivative of for theta and phi.
right. So let's say, but we already compute that one here. So it's going to be sine theta. So what else? Define the integrand. So we have to find out what f is, right? So that was 1, so that's why we disappeared, eliminate f, but we now have no constant function, so it's a z here. Can I just plug in z here? No. Why?
The dimension is different.
Right, dimension is different. So we're talking about the integration on theta phi plane. Z is related with theta phi. It's not independent to theta phi. So we have to plug in the formula of z in terms of theta phi. So what is formula? What is formula of f in terms of theta phi? Sine? Cosine, yes. This is z, right? And then, well, let's see. If you want to integrate, then you always have to use the Fubini theorem. So in order to use the Fubini theorem, you have to take the limit of each coordinate. So what's the limit of theta? So theta phi parameterized this upper half space, upper half sphere. Theta from theta?
Theta is from
0 to pi?
pi over 2.
Pi over 2, because pi gets you to the lower hemisphere. So pi over 2. How about phi? Right, 0 to 2 pi. So that goes here. And then this is for phi and this is for theta. So this is a constant according to phi. So 2 pi. And then 0 to pi over 2. If you make a formula for the sine cosine, this equals to 1/2 of sine 2 theta. So and then this is pi times 1 over 2 minus cosine 2 theta of 0 to 2 pi. So what is it? So it's minus 1 over 2 pi times minus 1 minus 1, right? So it's pi. Okay. So basically what we're trying to get is the mass of this upper sphere, upper hemisphere, whose density is getting larger at the top, but almost no density at the bottom here, because density is z. So if you take the slice or section of this upper hemisphere in the horizontal direction, then it all has the same density. But if you take the height, higher and higher height, then you have a larger and larger density up to 1 and 0, from 0. And the mass of that sphere, its hemisphere, is pi. Okay? Just problem for problem. Okay? Practice problem. No physical or real life implication, because there's nothing like this one. Okay, so let's summarize again, because these are the two most important parts in the integration part of the multivariable calculus. So summary is that if you integrate over a curve, then you can get that from simple integral, single variable function integral. And if you want to find out the surface integral, so the difference between the notation is that for the line integral, we use d small s, and for the surface integral, we use d large s. Okay? And for this part, we need a double integral. Over du dv. So not just remember the formula, remember how this formula is used to find out the computation. So here you should talk about the parameterization of the surface of the curve C, the C here, and F is two-dimensional surface, two-dimensional function defined on two-dimensional region which contains D. Okay. And also for the surface integral case, in order to find this surface integral, you need to have a parameterization of the surface. So I deliberately used the same notation for the set of a surface as a set and the parameterization of the surface. But don't be confused because of these two same symbol. And also our function should be a 3-variable function in this case. And the domain of function should contain this entire surface S. Okay. Okay. Simple. Just a simple computation. It's all boiled down to the double integral or some single variable integral. Now, this is the main part. Let's talk about integration of vector field. Okay? What is a vector field? So a vector field is a map from a set of point to a set of vectors. So probably you have heard about the vector field many times in physics, where you talk about the force field, magnetic force field, gravitational force field, electrical force field. So that force field gives you the direction of force at each point, right? So basically, that field is mapping a vector to each point. So if you have a point on, let's say, two-dimensional plane, then you want to find out at that point in which direction or in which magnitude the force is applied to. Okay, so that's the vector fxy. So I'm going to put an arrow mark over this symbol f, meaning that this is not just a scalar, but it's a vector. Okay. So you can consider your vector field as a part of a multivariable function, but there's a big difference between a multivariable function and the vector field. So vector field is a multivariable function, but there's more to it because if you take two multivariable functions, you cannot add these two functions. Okay? If you have a single variable function, you can add to get another function because the output of single variable function is simple number, so you can add numbers. But if you have two multivariable functions, that output is the pair of points or pair of numbers, there's no way you can add a pair of numbers. Okay? Only thing that you can think about adding 2 points is that when you talk about point vectors, right? Your direction vectors, which directs from the origin to that point. So, however, if you're talking about the vector field, it's a multivariable function. Having two coordinates for the vector, which corresponds to the point xy. And if you have another vector field defined on the same domain, let's say you have R and S, you can add these two vector fields to get another vector field. That gives P xy plus R xy and Q xy plus S xy. Okay? You can do this only because these are the vectors. Okay? you shouldn't do the adding between general multivariable functions. So don't do adding to multivariable function unless they are the vector field. Okay. And not only you can add to vector field, you can cross product to vector field if the vector fields are given by three-dimensional vector fields. Okay. But here we're talking about the two-dimensional vector field. We're not going to do that. But you can also take inner product. Right? But what you get after you take the inner product? You get a scalar number. So if you take an inner product of two vector fields, the result is not a vector field anymore. It's a multivariable function. Okay, so the result is pxy rxy plus qxy sxy. So this is vector field, but this is multivariable function. All right. If f, g, h are three-dimensional vector fields, then we can find out f cross g or f cross g inner product h or so on, or basically f plus g, and you can do anything here. Okay. Then operations such as these are possible. Now, we will have time to talk about these vector fields more. Let's talk about the line integral. So, have you heard of a line integral in electrical field in other course? So, where do you use the line integral? Find the potential energy. Right. So basically, yeah. So one point to another, you find the contour integral, line integral, to find how much potential energy has gained to the particle, right? So let's talk about the basic physical concepts here. So work is how do you compute the work? Or maybe more specifically, work done to the object is what? Well, let's say more elementarily, how do you obtain in the one-dimensional case? F prime d, right? What's F? Force of what? What kind of force? I mean, what force are we talking about?
Maybe gravitation.
Huh? Gravitational force. So that force should be applied to the object, right? Applied to the object. But if the force is applied to the object to the perpendicular direction, it doesn't move to that direction, right? So the force applied to the object to the direction of movement, right? And then multiply with the distance. Distance the object moved, and by that force. Okay? So if you want to find the work done to the object, first you have to find out what kind of force, in which direction the force you apply to the object, and then try to find the force that applied to the movement direction, and then try to compute the distance that moved by that force. Let's say I have a force field, like this one, and I have moved my point from here to here. And let's say at some point, force field has been applied to this direction. And I'm going to approximate the total work done to the object by moving A to B, from A point to the B point. So let's talk about the small work done on a small distance. So let's say I'm moving point from here to here. Maybe I can put that in Ci and Ci plus 1 as 2 points. And this particle has been moved because of this force field. Okay? So I have to find out the direction of force that applied to the movement of our direction of movement here. So let's see. This is my movement direction. Not entire force is applied to the movement, but only this portion has been applied to the movement, right? So this is only the part of the force that make this movement, okay? So how do we get this portion up? Let me erase other arrows, okay? So this is our force at Ci, and this is maybe I don't really need this I plus 1. Maybe I can just put that in Ct here. Okay. So at the time t, I'm at the point Ct, and I'm experiencing, the point is experiencing the force Fct, but this portion of force affects the movement to this direction. So basically this direction is C prime t. And how do we get this part? How do we get this portion of the force? Dot product. Good. So Fct dot C prime t. Is it enough? Times delta t. We are trying to get a vector using these two vectors. This projection vector using vector f and vector c prime. We're not talking about the delta t here. So we are talking about the instant direction at time t. So we only need to compute, multiply this vector with the cosine theta, right? So in order to find the cosine theta, you take the inner product, and then you divide it by the norm of vectors, right? So if you divide by the norm of f, then you only left with the cosine theta. You don't want that. You still want this entire f, so you have to divide by only the norm of c prime. So this is our projection vector, okay? So for someone who forgot about the vectors, the properties of vectors, let me say it again. So if you have A vector and B vector, and you have a projection vector, then this projection is A times cosine theta, with theta here. But you can get a theta, cosine theta, by A inner product B divided by A, B. So therefore we have A cos, sorry, it's not A cosine theta here. Sorry, what am I doing here? So we need A cosine theta, that's the length, and then we have to multiply that with the direction of B. So that's our projection vector. So therefore, the projection is A times cosine theta B divided by B is equals to this projection. If I just substitute cosine with this, is B square with A B, right? Right, so we have A, B, and did I forget something? So we have A, B, B, right? So we have B here, right? That's our projection vector. Let me write it again. So I think I made a small mistake. So we have, right, so we have scalar here, and then multiply that with C prime t divided by C prime t squared. That's our projection, okay? So small work done between this point to this point, let's say on C on the time interval from Ti to Ti plus 1 is approximately equal to the force on this movement direction times the what? Times the actual distance moved, right? So the total force on this direction, if you just take the scalar, this force is used as a scalar here, so is what? You take the scalar of this number, basically F Ct C prime t, and then you take the scalar of this, you take the absolute value here, you get C prime t. Okay? So if you take the absolute value, then it cancels out with one of the factors here. You're only left with the denominator of norm of C prime. So that's the force applied to that direction times what? Small distance. The length between Cti to Cti plus 1. Right? And this is equal to square root of, well, let's see. Well, some square plus square, but I will just make it approximately equal to C prime t times delta t. Okay, so delta t is Ti plus 1 minus Ti. Okay, so that's a small work done on these 2 points. If I add them all, then this is the entire work done from the point A to B. So total work is what? Sum over I of f c t. I'm sorry, so it's not just t, it's a ti everywhere, right? So I'm talking about at ti. Okay, so cti cti divided by c prime ti times c prime ti times delta t. Okay, so we have canceling. This just cancels out, and if this is approximate work, if you make a n goes, if you make the number of subintervals goes to infinity, then this sum is actually makes into total work. Oh. 뭐 꺼졌어요? 됐다. 저기 없어서. 내 방 가방 안에 저거 가져올래요? 이거 충전기. 내 가방에 있어요. 내 가방, 매는 가방 안에. So what's the total work? It's the integral of fct inner product ct dt. So t runs from the interval of t. Let's say this is when t equals to a, and this is equals to t equals to b. Then the integration is from a to b. Okay, but let's restate. Sorry, maybe. This is C prime, right? So where did I? So this is C prime. C prime here. Okay. All right. So I'm going to define my line integral using this idea. So let's say I have a force field fxy, or maybe defined this way. So it's d2 R2 be a vector field and this R2 means it's not a set of numbers, it's a set of points, it's a set of vectors, and D is lying inside of a set of points, two-dimensional points, and I'm assuming that C is a curve parametrized by CT XT, or maybe just the CT, okay? AV to R2, okay? So I'm assuming that my C lies in D, okay? So then, the line integral of this vector field over C is defined as the symbol. So it's a similar symbol, but you see the difference is that instead of ds, we have a ds arrow, and instead of just multiplication, we have a dot product here with a vector field. It is defined to be just a single variable function integration f c t dot c prime t dt. And what does it measure? What does it mean? It's called the line integral of f over c and what it means is the total work done. So it's tricky to say what is the who is doing the work, who is doing. So the work is done to the object, but who is doing the work? So it is done by the vector field. So work done by F to to the whatever the object is, because we didn't specify the object here. So it's the work by F along the curve C. Okay. So line integral is the work done by the vector field along the C. But it is important to say that in order to find the line integral of the vector field, you should not just specify the setup curve, but you have to provide it with the parametrization of the surface, of this curve. When you're talking about the line integral or the function, we said that it doesn't matter the direction of this parameterization, right? But in a vector field, if you integrate the vector field, the direction of parameterization matters to the integration. So let me write it as a remark. So remark is that the the direction of parametrization of the curve matters, which means if C1 parametrizes this curve C from P to Q, so let's say P, Q are the ends of C, and C1 parametrizes from Q to P, then let's say we have a same curve, but C1 is parameterizing from P to Q, but C2 is the opposite direction. What do you expect when you do the when you do the line integral of C1 and C2? Minus. Why?
All the side of cosine theta are some of them, some of all the cosine theta will be also.
Cosine theta?
We add all the f times s times cosine theta, and once once we integral this direction, then as opposed to this direction, then if it goes to this direction, then all the cosine theta, each cosine theta, all intervals will be
Right. So you're talking about this cosine direction, right? Cosine theta direction. So if you're moving opposite direction, you're talking about cosine pi over theta, which makes negative value. And also, that's a very, very good idea to say that. And then also, you can simply say that this C prime t is reversed. If you take the C1 and take the C1 prime t, then it's a negative C2 prime t. So you have a negative sign appears here. That's why you get a negative. However, if you keep the same direction, keep the direction of parameterization same, then does it matter to reparameterize your surface? Reparameterize your curve? Does it matter how fast you move your curve during this time period? No. So reparameterization doesn't matter to the line integral of the vector field, but direction matters. Let's give an example here. So let's say f x y is minus y x squared y squared x squared y squared, and okay. So basically this vector field is well defined except for the origin. So as long as I take the curve not passing through the origin, I can define my line integral. What kind of line do you want to take? Y equals to x. This line? Oh, I'm sorry. The y equals x is this line, but it passes the origin. So, or this one or the other. This one? Or maybe half circle, because it's easy to compute. So let's take a quarter circle here. So this is parameterized. This is C. And also, when you take the line integral of vector field, you have to specify the direction. And usually, if you're not provided any direction, then it means that you have to take the counterclockwise orientation. So let's say I'm going to take this parameterization. So Ct is cosine t sine t, and t is from 0 to pi over 2. So if I take the line integral of this vector field, by definition here, I am taking one single variable function integration. First, I take the composite, f composite C, and then it's confusing because it's the same notation with the inner product, so I'm going to write this way. And then inner product C prime t and dt. So let's plug in. So x is ct cosine t and y is sine t. So if I plug in there, the denominator is always 1. So it becomes minus what? Sine t. And x is cosine t. That's f. And then you take the inner product with fc prime t, which is minus sine t and cosine t dt. So this becomes sine squared plus cosine squared, which is 1. So I'm basically doing integration of 1, which is pi over 2. So maybe let's try, I haven't tried yet, but let's try what if we take the integration in this curve. Let's call it a different name. I'm going to call it dt. So how do we parameterize dt here? You start from 0. When t equals to 0, let's say we start from here and end it here when t equals 1. One minus t, comma, what? Straight line from 1, 1, t, right? So if you use that, then let's say I'm going to use D notation here. So plug in that there. So denominator is 1 minus t squared plus t squared minus t, and 1 minus t squared plus t squared. That's f, and then inner product with minus 1, 1 dt. So the line integral is from t from 0 to 1, right? So we get 0 to 1 of the sum of these two. So actually, they cancels out, right? So we get 1 minus t squared plus t squared 1 dt. I think I can do the integration. So let's see, we have 2t squared minus 2t plus 1 over 1 dt. But let's make it a complete square. So we have t squared minus 1/2 squared plus 1/2 dt, right? So I can replace that with what? Maybe I put 2 to 4. That's 2 over 4. So what should I replace that with? Substitute. For what? T minus 1 over 2. Tangent, right, tangent zeta. Okay. Try to do this. You will get the same answer, pi over 2. Okay. So we're going to talk about why did I know that this is pi over 2 later, the next time. But meanwhile, let me introduce another notation for our line integral. So let's say our vector field is given by PQ function. Then this line integral is also written as P dx plus Q dy over C. So this is another notation for the line integral. This notation is useful because it directly shows what the coordinate function of the vector field are, okay, P and Q. Here we have to use another definition. And the reason why we can use this notation is, think about this notation. If you replace PQ here, this is PQ inner product ds. But ds is basically you get ds by c prime dt, right? So this is a vector with a small portion of length. So this is how you can rewrite this. And then now think about c prime t here. So c prime t is x prime t, comma, y prime t in xy plane. So you can rewrite your this integration by p times p prime x prime, p times x prime plus q times y prime dt, right? And then you distribute your dt here and there. So it becomes p x prime dt, q y prime dt. Okay? So and then what? X prime dt is dx dt dt, this is simply equals to dx, and this is equals to dy. So that's why you get p dx plus q dy. So this is not only useful because we can see the pq directly, but also it's useful because you can actually separate these two integrals. For example, you can say p dx and q dy separate integral adds to the entire line integral. But what do you mean by p dx in line integral? So if you are given with this line integral, we are talking about the parameterization of ct. Although we ct are parameterized by xt and yt, we're only talking about xt part, x prime t dt. Okay. Of course, we have to plug in xt and yt for p, but we are not considering the direction of y on this curve. So we are only talking about the t here. Then also you can do the same thing for q dy. So this notation makes some calculation easier. Okay. And another good thing about this notation, that p dx plus q dy, is that you already have seen this kind of notation in the differential equation, of course. So it's like total differentiation. So if you can find out some function, two-variable function f, whose total derivation is equals to p dx and q dy, meaning that if you take the partial derivative of f in x is p, and partial derivative of y is q, then this is equals to some simple df. So you're integrating your df over c. So now you have to think about meaning of what this notation is. So whenever we say dt, for example, or dx, for example, that's the infinitesimal increment of that value, right? So we are talking about this adding all the infinitesimal increment of f over the line. That means we're not care about where we are. We only care about at each point I'm going to increment or decrement of f, measuring those increment and decrement of f, and then add them all. That means I only care about end value of this f and starting value of f all along this curve. So let's say if c is from p to q, then this integration of df is equals to just simple difference between the end value and then the start value, right? It's the same thing that you will have integration of, let's say, dx over 1 or any point a, b here. So this is simply b minus a, right? Because you're just taking a value at b and value at a, right? Here we're talking about the value of f. So the value of x is at a is a, so that's why we have ba here. But we need a value of f at the starting and end points. No matter how this curve looks like, we just have this. So this happens only when we can get this p dx plus q dy by total differentiation, total derivation. And the reason why I'm kind of giving a hint that we get the same answer for this vector field in line integral is that this vector field has this coordinate function which can be obtained by this total derivation. We say that kind of vector field, a vector field that admits a potential function. So that function f is called the potential function for the vector field PQ. So that's going to be the topic for next class. And once we talk about those parts, and then we're talking about the flux of the vector, which is the surface integral of the vector field. And if you know the line integral and the surface integral of vector field, now we are ready to talk about the Green's function, Green's theorem and Stokes theorem, and then divergence theorem. And meanwhile, we're going to talk about divergence and curl of the vector field. So before we finish, let me mention that we have not many weeks to go, so I'm going to give you a deadline until December 3rd to finish your homework on question and project and the programming. So after December 3rd, I'm going to close all the Notion pages so that you cannot edit anymore. So then I'm going to mark your assignments. We're not going to have a final exam. So yeah, so do your homework, please. And if there is I'm going to give you some opportunity to present your report or present your assignment results. If I see that it's exemplary work, then we will do that on the last week of our semester. Okay. All right. So thank you very much, and see you on Tuesday.